Hey guys, last time we talked about series circuits and a little bit about parallel circuits, or should I say resistors arranged in series. And here's an example of three light bulbs, and they are arranged in series. And what it means to be arranged in series is that by their arrangement, their currents have to be the same. In this case, they're placed one right after the other. So when I'm going to turn on the whole circuit here. Let's actually turn that one off. When I flip this, none of the electrons can move because there's no way for them to get from the negative side of the battery around to the positive because it's broken there and broken there. If I flip this switch, this one turns on. If I flip this one, these three turn on, and these three are said to be in series with each other because by their arrangement, the current flowing through this light bulb has to be the same as the current flowing through this light bulb and this light bulb. For instance, if a bunch of electrons are moving through this light bulb, well, there couldn't be more or less going through this one, otherwise electrons would be like piling up somewhere in the circuit. Electrons don't like to be near each other, they're not going to pile up someplace. So it's kind of like a chainsaw. Right when I flip this switch, all of these electrons start moving around at the same time. If I flip this switch, now we're going to, this one off. When I flip this switch, they all move around. Right? They all start moving at once. So it's not like, the electrons have to get from over here all the way over there. There's already electrons in the wires. Okay, so that's series. And let me review a few things actually about resistors in general. Okay, so if we have a resistor, the wires are generally very low resistance. Okay, but I'm going to make their resistance just a tiny bit higher so we can see some things. Actually, I'll have it play here. Let's have this, we'll have this one going. All right, so 0.9 amps are flowing around this circuit. If I make the resistance higher of the wires, the current goes down because there's more resistance. These wires have more resistance. But watch what would happen if I would make one of these wires, say, longer. Okay, as I make it longer, it has more resistance and the current goes down. Okay, so the resistance of a wire, a piece of metal, is based on its length. As it gets longer, there's more resistance. It's kind of like adding two wires together. Their resistances would add together. You could also change the width or the diameter of the wire. I can't really do that. I can click on this, but it doesn't let me change its resistance or anything except with this. But if you were to make the wire bigger around, its resistance would go down and the current flowing through this circuit would go up. If I were to make this wire very thin, then that would be, its resistance would be high. Okay, so more fat wires are low resistance and short wires are low resistance. The thinner and longer it is, the more resistance that piece of that metal is going to have. Okay, so that's a review of resistivity of metals. And I'll actually review a little bit. We talked about Ohm's law. There are a lot of electronic components obey Ohm's law, where if I take this voltage and I double it here, the current is 0.9 amps. If I double the voltage to 18 volts, the current also doubled. This simulation pretends like that's true for light bulbs. In reality, if you notice that light bulb got brighter, metals actually, as they get, so this light bulb is glowing because it's hot. So if this light bulb is glowing brighter now, it's because it's hotter. And actually metals, as they get higher temperature, the resistance goes up. So they are not ohmic. This light bulb is not really ohmic. It may be when it's on pretty hot, it may be pretty close to ohmic. So maybe we still consider them ohmic when it's on. But if I were to, make this go way down in real life and measure its resistance, it would be much less. So light bulbs are not really ohmic, and metals themselves generally, probably for that reason, are not completely ohmic. But these wires that we have are so low resistance to begin with that we don't really worry that much about these wires. We don't really worry about the resistance at all. It's very small. In this case, we have it all the way down to 0. Another bit of review for you. We're showing the real current as electrons moving from the negative side of the battery to the positive side of the battery. So this is the positive side. Electrons are going this way. Conventional current pretends that positive charges are moving. They didn't know anything about protons, neutrons, and electrons, so conventional current imagines charges flowing from the plus side of the battery around to the minus side of the battery. and I can turn this one off, and the current shuts off altogether. There's no current flowing. If I connect this one, now current is going this way around. So conventional current is different from what's really happening because conventional current pretends like positive charges are moving around the opposite direction that electrons are really going in the circuit. Okay, now we're gonna mess with some things here, and we're gonna worry about series first. Okay, so I'm gonna leave this. I'm just gonna just forget about this altogether. I could just break it, but I'm not going to. So let's say I break this here. The whole circuit shuts off, right? Because now the electrons cannot get around, so the electricity shuts off. And I'm actually going to remove this bulb for a second. Okay, and you will see that now we only have 2 light bulbs in series. This one has been removed altogether, and the current is 0.45 amps. Okay, so what would happen if I insert this light bulb back in? What happens to this current? It's 0.45 amps. So break it. I want to twist it. And put this guy back in. The current goes down. Why would the current go down? Well, if the current goes down through this path here, from going from there to here, that means the resistance must have gone up. So when we take these light bulbs, right now they're having them as 10 ohms. They're each 10 ohms. When I go like this and I have 3 bulbs, these resistances, when they're in series, they just add up. It's just 10 ohms plus 10 ohms plus 10 ohms makes 30 ohms. And this is a 9-volt battery. And if you take 9 volts, that's V divided by I, which was 30. 9 divided by 30 gives us our 0.3 amps. Because, well, 9 divided by 30 is the same as 3 divided by 10. So 0.3 amps. Okay, and if I were to remove this guy again, then instead of having 30 ohms, we would only have 20 ohms. And so 9 volts divided by 20 is the same as 0.45. Okay, so that's how things work for series circuits. When you add another resistor, you're adding resistance to this part of the circuit. And so when the resistance goes up, the current goes down. Okay, that's true for series circuits. Now, is this light bulb in series with these other light bulbs? The answer is no, it's not in series, because the current going through this is not, by the arrangement of the light bulbs, is not the same as the current going through this. In fact, these guys can have completely independent currents of each other. These guys, if I take this and I could even, mess with its resistance, it doesn't change this current at all. Okay, I could turn this whole part of the circuit off. It doesn't mess with this at all. And this is assuming that these wires are, in real life, it would change maybe slightly because this battery can only provide, well, if the wires are low resistance and your power source is very good power source, it's not going to change this at all. Okay, just like the simulation is showing. But this one is not in series with the other ones because it has a different path for the electrons to take. Okay, so this one is not in series with these 3. In fact, the word we use for these guys is this light bulb is not in series with these 3. It's said to be in parallel with these 3. Okay, now it's not in parallel with each one of them. It's in parallel with this box, if you will, all 3 of them together. So what does parallel mean? Parallel does not mean that these lines are parallel, contrary to what you might believe by the name. Okay, what parallel means is this. See how this guy? I'm just going to stop this thing right here. See how this part of our resistor, our light bulb, it's connected by wires. When I close this switch, it's connected by good low resistance wires to some point over here, and so is this light bulb, right? And these 3, if I take them as one box, one group of resistors, the other side is connected over here, and this other side is connected over here. So this light bulb is connected by good low resistance wires to this location, and by good low resistance wires to this location, and so are these 3. If I could draw a box around them, they're connected to this location over here by wires, and they're connected to this location over here by wires. So they're said to be in parallel, and if they're in parallel, and we use a voltmeter, then across these three, if I do all of them, there is going to be 9 volts across them. And over here, there will be 9 volts across them as well. Okay? Now, suppose I were to place another resistor in here. I'm going to use a real resistor here, not a light bulb. And connect this on. Now, these are not 9 volts anymore because some of the voltage is going across this resistor. In fact, we can figure it out. From here to here, 9 volts. That's the battery is 9 volts. But from here to here, there are... Actually, I should... Yes, if you want positive numbers, I should start going the other way. There are 5.14 volts across this resistor here. Okay? So you put the black lead closer to the negative of the battery. So if I go... So 5.14. So what is this across all of these? It's 3.86, the rest of 9 volts. And these guys will each share this 3.86. So 3.86 divided by 3 is 1 point something. So we'll see 1.29, 1.29, and 1.29. That's only true because these three are the same resistance. If I were to, we're going back through series. If I were to change the resistance, let's make this one, what were they, 10? Let's make it 20. This one is going to now have, it has 2 volts, where this one has 1 volt, and this one has 1 volt. So in series, the resistors do not have to have the same voltage. If they have the same resistance and they're in series, they'll have the same voltage, but that's not true in general. If they have different resistances, they can have different voltages because they all have the same current, right? So all have the same I, but if their R's are different and we do V equals IR, you take the same I times a different R, you get a different voltage across it from one side to the other, okay? But look what happens up here. This is now 5 volts, okay? If I, see, this is going to change. This just gets a little more complicated when you have a resistor down here. So I'm going to remove it now. Just connect this back, okay? But if there's low resistance down here, and I mess with this, if I turn this on or off, it doesn't change the 9 volts across this light bulb, because this light bulb is directly connected to the battery on both sides, so it gets all 9 volts. Now, with that resistor removed, these are directly connected to the battery on both sides, so they get all 9 volts. But this one is said to be in parallel with these three. And similarly, I'm going to show you something like this. I have the current shut off, so we're not going to see the electrons, okay? Right now, nothing's flowing because there's no path. All three of these switches are open. So I could turn this one on. This is more like your house, right? You can turn on all these light bulbs or turn them off. Okay, but I'm just going to do this to make it a little easier to look at for a second. Is this light bulb in series or in parallel with this light bulb, or neither? They could be neither in series nor in parallel. Are they directly connected on both of their sides to the same spots with good low resistance wires? And the answer is yes. This is connected to there, and so is connected to that same spot by good, when I close the switches, they're connected to, here, close them. This is connected right here, and this is connected right there. This is connected over here, and so is this. In fact, both of these are not only in parallel with each other, they're in parallel with the battery, so they should get all of the voltage. And the voltage, I believe, is still 9 volts across our battery. So if we go in here, yep, 9 volts. And each one of these will get 9 volts. Okay, now what if I were to do the same thing I did before and put in a resistor here? I'm going to make this a little wider. Cut it. And stick a resistor in there. Now, these are not getting all 9 volts. There's 9 volts across the battery, but the resistor right now happens to be taking 3 of those volts. Okay? Oh, I forgot to switch it. There we go. 6 volts, sorry. The the resistor is taking 6 of the volts, but these guys are still going to have the same voltage because even though they're not in parallel with the battery, they're not getting all of the voltage of the battery, they're still getting the same voltage. They're connected by wires to the same location on this side, and they're connected by wires to the same location over here. Okay, now here's a question for you. When I connect this, will this light bulb be in series with this one, in parallel with this one, or will it be neither in series nor in parallel? So, is it connected by wires to the same location this is on both of its sides? When I close this switch, it's connected by wires directly over here, and it's connected by wires directly to this spot. These are called nodes where the wires come together. And this one is also connected to those same spots. So it turns out, even though that the wire is not in a parallel direction to this wire, these two are still in parallel with each other. They have 2.25 volts across that light bulb, 2.25 volts across this light bulb, 2.52 volts across that light bulb. Why did that voltage change from before when I added this? Watch. Well, it's because when I do this, when I close this switch, it doesn't change this, it doesn't change this, but it does change the amount of current flowing through the entire circuit. Okay? So when the current goes up, the voltage across this guy goes up because he's in series with the battery. Whatever current flows through the battery has to flow through this resistor. Okay, so when I switch this, the total current goes up, which means the voltage, I didn't switch it, across this resistor goes, the current through the resistor goes up, so the voltage across it goes up. But that gets more complicated, so let's just get rid of this. Most of the time we just have it like this. Okay, so these three light bulbs are in parallel with each other, even though this line is not a parallel line to this, because they're both directly connected to, this is actually in parallel with this light bulb, and the battery. All three of these are connected directly to the terminal of the battery. Okay, but two resistors are in series if they're connected on both sides of them to the same location in the circuit with good low resistance wires. Okay, now I'm going to shut this whole thing off. And actually, let's do this. This could be like a circuit breaker. Okay, your home is wired in parallel so that it's easy to turn on, one thing, another thing, plug in a toaster, right? And the toaster turns on. Whatever you want to do, you can hook up things, as many as you want on or all of them off. But watch what happens to the current. As I keep turning things on, the current through this wire down here gets bigger and bigger and bigger. Okay? So if you turn on too many things, the wires heading back to, the wires going up to the power lines, the current in those wires keeps going up and up and up and up and up. If you keep turning things on and on and on and on. And if that current gets too high, these wires can literally melt. And when they melt, they can, melt the rubber around them. They can start fires in the walls. So somebody originally a long time ago, they didn't have a circuit breaker, but I need to borrow a wire here. They had a fuse. Okay, and a fuse is just like a little wire in there, but it is a higher resistance than everything else, and it is real thin and it's easy to burn. So what happens is if you turn on too many things, and the current gets too high, and these wires might start to melt. These wires here that are getting all of the current, this melts or burns. When it melts or burns, it breaks the circuit, turns everything off. It protects these guys from getting too much current or burning up themselves. Because what can happen sometimes, that was not what I wanted, is what happens if, say, this wire breaks somehow, okay? This may not work, but if it touches over here, watch what happens. Before I connect it, the electrons are going to go through this wire, through this wire, through this wire to here, and they're going to get all the way around the circuit without going through any light bulbs, without going through any resistors. And that is dangerous because electricity will flow like crazy. Okay? And these wires can melt or burn. Okay? So what will happen is, as this current builds up too much, this wire, the fuse, will burn. Okay? And stop the whole circuit, protect these wires from burning. And if this was inside, say this wire, say this is like your toaster, some wire inside the toaster breaks, it'll protect the wire, the toaster from burning up. The sides of the toaster or something else from burning up. And it gets more complicated in real circuits. You can have a lot of stuff inside just the toaster. This toaster could have a bunch of electrical components and you can burn something up. The bad thing about fuses are you have to replace them. So somebody came up with what's called a circuit breaker. And the circuit breaker, there we go. Circuit breaker works like this. If the current gets too high, because you keep turning stuff on, instead of burning up, it will open didn't let me do it. It will open the switch and turn everything off. So circuit breaker is reusable. I showed you my circuit breaker on my home a while ago. Okay, so that's a review of circuit breakers and fuses. And then let's look and see what happens for resistors in parallel. These are all in parallel right now. So I'm going to hook this up and turn this on one by one. Okay. So the current right now is 0. The electrons can't get around. I'm actually turn this off to make it a little easier to look at. If I turn this on, the current goes up. The total current goes up to 0.9 amps. If I turn this on, what's going to happen? Well, actually, I'm going to change this guy's resistance just to make the numbers different. Sometimes students get confused when things stay the same. They think it's always the same. So I'm going to turn this on, and this guy's going to get 0.45 amps. All right, half the current because it has double the resistance as this one. But they're both getting the same voltage. They're both getting, in this case, all 9 volts. Okay, so 9 volts divided by 10 ohms is 0.9. 9 volts divided by 20 ohms is 0.45. But then these currents are going to add together, right? When this current comes down this way, it's going to add to this current coming this way to make a total of 1.35. What happens if I turn this on? Well, now electrons can not only turn and go this way or turn and go this way, they can come up here, and this one's going to have a current. And the total current went up from 1.35 to 2.25. So if the current went up, what happened to the total resistance of our circuit? Imagine you're the battery, right? And you don't know anything. You just know you're connected to these wires. You don't know what's going on. And all of a sudden, instead of having 1.35 amps, you're pushing around 2.25 coulombs every second. It feels to you like, hey, I was pushing just as hard before, but now I'm pushing more current around. It got easier for me to push current around. So the resistance of this entire circuit went down when I added a new resistor in parallel. That was not true in series. Back here when we added the third resistor, the total current went down. In parallel, when you add another resistor, the current goes up, the resistance goes down. And the reason is because we not only added a new resistor, we added like a new lane of the freeway. Okay? So if I take this and turn it off, no cars or if this is like water, no water can go through those pipes. But if I add another pipe in, I can pump more water around and the current goes up. It's easier to get current to go around. Okay, so in series, when you add a new resistor, the total resistance goes up, the total current goes down. In parallel, when you add a new resistor, the total current goes up, the total resistance goes down. Okay, and then I'm going to show you something what would happen if I put this. I'm going to have this switch open for right now, but I'm going to connect this here, and I'm going to connect, I do have one more wire. Like this. I didn't flip the switch yet, but what happens when I flip this switch? Well, nothing happened, and why is that? Because no electrons want to go up through this light bulb and over through this light bulb, because this is just a straight wire, right? There's very, very, very little resistance going from there to there. So this didn't do anything. Okay? But what if I were to open this switch and not let the electrons go through there? They would have to go through this light bulb, they would have to go through this light bulb as well. Okay? So when I open this switch, they can't flow at all, but when I close this one, now they're going this way. See it? So these two resistors right now with this switch open, these resistors there and there are in series, because whatever current flows through this light bulb has to go through this light bulb to get around to the positive side of the battery. So right now these two resistors are in series. Their currents would be the same. I'm not going to put the current, I'm not going to show you, break this and show you the current, but these currents are the same. If I go like this, they're not in series. In fact, this one turns off. I could pretty much just cut it out of the circuit. And then if I go like, if I turn that, get rid of this, and these guys, now this one is in parallel with these two, even though the wires are not parallel, like parallel lines, this one is directly connected to this side and directly connected to there by wires, and so is this one on both sides. Actually, so is this one. It's connected to that same spot, and so is the batteries connected to that same spot. So right now, these three resistors, the three light bulbs, and they're all three in parallel with each other, and they're all in parallel with the battery, so they're all getting all 9 volts across them. Okay? If I were to open this and close this, this one still gets 9 volts. It didn't change. It's still in parallel with the battery. This one is still in parallel with the battery, but this one is no longer in parallel with the battery. It's in series with this one, right? These are now in series. And instead of being 10 ohms, their resistance of this path is 10 ohms. They're in series. 10 ohms plus 10 ohms makes 20 ohms. Okay? So they are going to be sharing the 9 volts. And they each get 4.5. And actually, maybe I will do it this time. I'm going to break this and shove this guy. Oh, I could just get a new one. Easier to get a new one. Okay, so when I turn this on, this one, remember, if we change the resistance to 20 ohms, when I turn this on, this path also has 20 ohms of resistance, because 10 ohms plus 10 ohms makes 20 ohms. So if you notice, the voltage across these guys is 9 volts, just like the voltage across this one is 9 volts. This light bulb itself is 20 ohms, but these two together make 20 ohms. So the same voltage, 9 volts across them, 20 ohms total through this path, and 20 ohms total through this path gives us the same current. Okay, so now are these two light bulbs are in series with each other. Are they in parallel with this one? Well, it depends on what you mean. This light bulb is no longer in parallel with this one. It's not directly connected by wires to the same location. Ready? It's connected directly by wires to here, and so is this one. But it is not directly connected by wires. Oh, I have to go through a light bulb. It's not directly connected to over here, right? You can't go this way because this is shut off. So it is not directly connected by wires to this location because we had to go through this other light bulb. So this light bulb is no longer in parallel with this one. Right now, it's neither in parallel nor in series with this one. It's neither. This light bulb right now is in series with this one. And together, if you draw a box around both of them, they're in parallel with this one because they're directly connected on this side to there, and they're directly connected on this side to there. So these two light bulbs together get the same voltage as this light bulb and this light bulb and of the battery. These two light bulbs together, as a unit, are in parallel with the battery. Okay? And the last thing we'll review is what is current? It's really electrons moving, right? Conventional current pretends like it's positive charges that are moving the opposite direction. But what does this number mean? 1.8 amps means 1.8 coulombs of charge are flowing through this location in a second. And a coulomb, if you remember, I think it's 6.25 billion electrons. We came up with that because the charge of an electron is 1.6 times 10 to the negative 19 coulombs. So we could figure out, if we take this 1.8 amps, right, that's coulombs per second, we can convert the coulombs into number of electrons and figure out how many electrons are going by every second. You have a homework problem that's kind of the reverse of that. So this would be 1.8 coulombs per second, and then coulombs on the bottom. Actually, let's just move to the paper. So this is not quite like your homework problem. Your homework problem is in reverse. 1.8 amps. Oops, sorry. 1.8 amps is the same thing as 1.80 coulombs per second. And then we're going to make a kind of a table out of this. Put coulombs down here and electrons. 1.60 times 10 to the minus 19 coulombs is 1 electron. And we can figure out how many electrons per second are going through that spot. And that's one way to solve it, but the better way probably was just to use the definition of current is the amount of charge going by in a certain amount of time. So in your homework problem, you're actually trying to find the current. Okay, so you got to find that charge and divide by the time. But remember, amps is coulombs per second. So you're going to find that, what's basically find Q. All right, Q is, the time they gave you is 1.1 minutes, but you don't want minutes, you want seconds to get amps. And you have to find that charge, and they gave you the number of electrons. Okay, so you have to convert from electrons to coulombs instead of from coulombs to electrons. So convert from number of electrons to coulombs, take that number and divide by the 1.1 minutes, and you'll have your answer. And we'll stop there for now. I know this video was longer than normal, partly because we did some review, because it's been a while for some of us since we were talking about this stuff before spring break. So hope you liked the video. Hope it helps make sense. Please ask questions if you have them, and I'll talk to you soon.